and ask yourself, can there be a super strong conductor that conducts electricity without losing any of it? Because the biggest problem right now is all those electric wires you see, they lose electricity as they go down the wire. They go to the air and other things. And to heating the wire, mostly to heating the wire. So can you have an object that doesn't do that? That doesn't heat the wire, it just lets the energy flow without losing it. And that would be called a superconductor. Now, why I'm interested in superconductors? Because loss of energy means loss of money, but also means that you have to produce your power, electricity, pretty close to where it's being used. If you produce electricity in Maine and try to ship it to California, by the time it gets to California, well, let's put it this way. It's like transporting ice in the back of a flatbed pickup truck. By the time you get from Maine to California, out of a big, huge block of ice, you have a little ice cube left. And unless you can sell that little ice cube for more than the entire block of ice in Maine, it's not worth doing that transportation. It's very inefficient. But if you can create a device, say a refrigerator, then you could take that ice and move it without losing ice. And that's the equivalent of a superconductor. So basically, you build a conductor that doesn't resist the flow of electricity at all. Conductors do, but they do it on a very small scale. Insulators have very high resistance. This is kind of leading me to our lecture for next week. Probably get the idea, the picture a little bit. Right now, our current level of technology for superconductors, right now we can only do it at very low temperatures, and it takes a lot of energy to cool things to that temperature, and it's not practical to have long wires that are cooled to minus 300 degrees Fahrenheit, and so right now they're not practical, but the hope is in the future that we can create alloys that will allow objects to be, or metals to be superconductors at room temperature. And if you can do that, then you can build all of your electric grid out of superconductor material, and it'd be much more energy efficient, allow us to transfer electricity, which means we'd have to produce less energy. We're talking by a factor of 3 possibly here. And so that's 3 times less fossil fuels used, boom, right there, without actually having to do a whole lot other than 2 people power lines in the United States. But then we can build a smart grid. So maybe that's what we're waiting for right now. Now, suppose you wanted to save a charge for later. It's nice saving things for later. Oh, I didn't need all that ice cream cone. I'll save it for later. You put it in the freezer. So how do we build a freezer for chargers? Because if you're doing solar power, for example, if you don't use it, you lose it. What about for computers? You have charges flowing through the computer, but then they flow right back out again. Sometimes it's nice to store some charge so that you can use it a little bit more charge later, or a little bit less charge some other times. So collecting the charge requires a device. Well, you can do a battery, but usually in a computer, we use something called a capacitor. A capacitor is a pair of sheets, and what they do is, as the charges go onto the sheet, they stay there and they induce the opposite charge on the other sheet, which now creates a lot of energy. So you store energy within the capacitor. And then when you want to, you can then discharge the capacitor, and that energy flows through, and you get that energy out. This is usually used for tiny parts of the circuit, because it takes time to charge and discharge the capacitor, and based on certain time cycles that we won't get to in this class, because this is an algebra-based class, and requires square roots and stuff like that. So, but there's a limit. Kind of like holding water behind a dam. If I let too much charge build up on my capacitor, the capacitor will overflow. It will discharge automatically. We see this all the time. When clouds move around, against air. This allows them to create a charge. So they end up with a charge on the object, on the cloud. If the charge in the cloud becomes too great, it discharges, and that's lightning. So lightning is the discharge of a capacitor where one end of the capacitor is the cloud and the other end is the ground. So you get a flood. You get overflow, if you will. So there's a limit to how much charge you can create in a specific capacitor. Now, if you want to increase that limit, you either build a bigger dam or bigger capacitor, which is expensive, or you put something in the capacitor that shields the charges so that one side of the plate thinks the other side has less charge than it actually has, so that there's less force. And this is called a dielectric. So dielectrics allow you to hold more charge before the capacitor overflows. And there's something called the dielectric constant, and that dielectric constant is how much more charge you can actually hold on the capacitor. Water, for example, has a dielectric constant of 80. So if you put water in between two plates, the plates can hold 80 times more electricity, and the capacitor is 80 times stronger. All right, so to wrap up, what have we learned this week? We've learned how to find the electric field and electric force. We found how to do the electric potential. We've seen applications for electrostatics, such as conductors and inductors, and we've seen how to store charge and increase the stored charge by using a dielectric. So that's all for this one. Next week, we will cover circuits. And even if it's a non-algebra based class, circuits aren't so bad. A lot easier than this chapter.